Okay, we good?
Yep.
Okay, so welcome to Intro to Programming. Side note, we will be recording this lesson so that you guys can reference it in the future if you ever need to. So I'm Lisa, I'm a senior. This is my third year in robotics, and I'm the lead programmer for 9432 Blood, Sweat, and Gears.
Hi, my name is Jacob Marinas. I am a junior. I've been in robotics for now 3 years, and I am the lead programmer at Patriotic Robotics. So without further ado, we'll get to the content of our slides. Okay, so we're here. We're in this programming workshop. What exactly is programming? So programming is just the act of writing computer programs. And I know what you're saying. Why are you using program to describe programming? Well, programs are simply just a set of instructions that you give to your computer, and your computer is going to read it, and it's going to be like, oh, I have to do this. And it's just going to do exactly what you tell it to do. So on the right, you can see that I've created a little GIF, however you pronounce it, of some commands that you might give to your robot that it'll do. And these combinations of commands help you as a programmer to solve a problem. And this problem doesn't specifically have to be about robotics. So in this case, our problem is making the robots move, but other problems might have to do with like perhaps making an app or a game. Programming is definitely used a lot in like the medical field, obviously in engineering. It's used basically anywhere where there's a problem. All right, next slide. So here I created a little diagram, kind of like a flowchart of how your ideas and concepts that you have as a programmer come to fruition in your hardware and your devices. So you as a programmer, you're programming in what's called an integrated development environment, or IDE. So it's basically just what you write your code in the same way that you write your essays in Google Docs or you create your presentations in Google Slides. It's the same thing with an IDE. And you can see on the left, we have the Android Studio icon. That's what we use in robotics, but we are going to be using a different IDE today. And in this IDE, you are going to be writing code for a program file. And like I said earlier, a program is just a set of commands, a set of instructions that this computer will read and will do exactly what you tell it to do. You'll write it in a specific programming language, which we'll get to that in the next slide. You can see that little icon. That's the icon for Java, which is a programming language that we use in robotics as well. And so this program file gets interpreted by our little computer, but it's going to need some help. So it has what's called a compiler, which will turn our human code that we've written in our program file to machine code. So basically ones and zeros that this computer can understand. And this computer will take that input of code and will produce an output on whatever device you might have, whether it be our monitor or in this case, the robot, but more specifically the hardware. So in this case, our computer may be our control hub or our phones, and they're gonna produce an output, an electrical signal to our motors and servos to turn a certain speed or go to a certain position and whatnot. And now we'll get to our programming language slide. So programming language, when you think about language, there's English, Spanish, French, there's all those different languages around the world. And a programming language is actually super similar to, regular like linguistics in that there's vocabulary, grammar, and just you can make coherent thoughts, sentences. So I'm just gonna read off the slide. So every programming language has a set of commands that the computer can understand, and that's kind of your vocabulary. And if for computers to understand your instructions, you need to follow syntax rules, which is your grammar. And together you make a programming statement, the sentence. Now, obviously, you don't give a computer only one instruction. You have a lot of commands that you give to your computer, which will then go on to solve a problem such as, a robotics competition. So let's get to the next slide. So here I created a little visual as to kind of what our little statement can be broken down into, as well as just the integrated development environment itself. So you can see that we have our little file name right there. It has the extension py, which you'll understand in a second. We have our statement on our second line, which I've broken it up into 3 parts. We have our instruction, which is to print. We have our syntax, which is just the parentheses. And then we have our parameter, which is, I guess I would say like the content of the sentence. So in this case, hello world. And this parameter gets passed on to our instruction to print. And you'll see that this code, this input will be produced to an output, not on a robot, but instead on our monitor, more specifically the terminal, and you'll see that it says hello world. You can change this parameter to be pretty much anything. Instead of hello world, you can put like hello Risa, and instead of saying hello world on the output, it's going to be hello Risa. Next slide. Just like how there are many programming languages around the world, just like how there are many languages around the world, there are different programming languages that are designed for a specific purpose. So there isn't just, like I've said before, Java, but you'll get to know other programming languages such as Python. There's also languages like C++, C Sharp, like Ruby, SQL, all those different things. And these programming languages have their own syntax and instructions because they are built for a specific thing. Like these programming languages are better for working with numbers, while some are better for web design, such as like HTML and stuff like that. And with that, I'm going to pass this on to Risa, who will be continuing the presentation.
Hi guys. Okay, so at least until we're able to get back to school, we're going to be using primarily Python for programming. It's a very beginner-friendly language and it's easier to read. And I personally really like it because it doesn't have as many restrictions or like syntax rules that you have to follow. And so that's less stuff that you have to keep track of as the programmer. Generally, it's used for data science and web development and whatnot. And then this is the logo over here. So for IDEs, integrated development environments, generally programmers will use them to write their code in. They have several built-in tools that enhance the experience and make it easier on you as the programmer, such as autofilling. They can also detect issues in your syntax before you run your program, so that like it prevents you from running into debugging later on. Technically, you could write code in a text editor like Notepad, but because it doesn't have the built-in tools that the IDE has, it's just really tedious and wouldn't recommend it. So over here on the side, we have a Visual Studio Code, Eclipse, and Android Studio, which we use. So programming in FTC, well, what's the connection? So as you guys saw in the game video, we have our autonomous period, our 30-second period of time where the robot has to run solely on pre-written instructions, and teleop, where your driver is able to control the robot with a controller. So here we have just two flowcharts of essentially what processes your code could potentially go through. So over here on the left, we have your autonomous. So essentially, when you start your program, you have to define all the pieces of hardware that you're going to be using. So your motors, your sensors, everything. And so with the autonomous period, you have to wait to press a play button before the code will actually start running. So if you haven't pressed the button yet, it keeps looping until you do press it, in which case it's true, it'll start running the code. So over here, we essentially have all of our different instructions that we can give the robot. And what's really nice is that, as you can see here, your code can branch out depending on the situation. So if you remember from the game, we essentially have, after randomization, we have 3 potential different scenarios that our robot might have to execute. So it's nice to be able to branch out like that. And so once it does finish executing that particular set of code, your program's over, it'll stop running. For teleop, though, once you start and declare all your hardware, essentially it's going to keep looping until you press the stop button. So as you can see over here in the diagram, it's going to keep looping through. From my understanding, essentially it's checking these conditions over here every like 20 or so milliseconds. So essentially every 20 milliseconds, it's checking, okay, on the controller, am I clicking the left stick? Or am I clicking a bumper? And if it is true and I am pressing this button, it'll essentially run that designated piece of code. So that's really fun. And then once you do press the stop button, the program ends. So because we're in quarantine, we can't really test any code on our robots because, you know, quarantine. So instead, we're going to be using a simulator. So simulators are fun because we're able to replicate programming and testing code, but in, I guess, like, not, it's a simulator.
Yeah, it's kind of self-explanatory.
Maybe not the most accurately, but you do get an idea.
Yeah. So specifically, we're going to be using VEX VR, which is a web-based IDE. So you're able to run it on your Chromebook, which is really nice because, like Tyler mentioned earlier, not all of us have access to a personal laptop where we can install Android Studio. But it's really nice. It has a lot of features, and we're able to use Python as the language that we use to code this cute little virtual robot. So yeah, if we go to vr.vex.com, you guys can follow along. Okay, just checking. Everybody can like see this, right?
Yep.
Okay.
Yep, you're good.
Thank you. So as you can see, it does allow you to use block coding as well. We won't be using block coding at all for robotics, but I think it's helpful just for like conceptualizing. So as you can see over here, we have our, I guess, playground, our robot, right? So hypothetically, if I wanted to drive forward, I can just click and drag the forward block and specify an amount of, I guess, distance that I want to travel, right? And if I click run, it does it. Wow. So if you'll notice, each, I think like 100 millimeters is essentially a block. But yeah. Okay. So I'm just going to be going through like the basic mechanics, and then I'll hand it off to Jacob after. So for instructional purposes, I'm going to slow down the velocity of the bot so that you guys can see it move. Okay. And then what's also really nice about VEX VR is that it has a pen feature. So I can actually, as you'll see in a few minutes, or I guess few seconds, I can actually draw inside this simulator. I'm a clown. Okay, hold on. Forgot to move the pen down. Huh. So as you can see, you can actually like draw inside the simulator, which is really nice. So that's to go forwards. Hypothetically, if I want to go 90 degrees, I can turn. So I personally suggest just using the turn right feature, because turn to rotation is a little bit more awkward to understand because it uses sensor readings from the virtual robot. So if I run this, wow, it turns.
Ooh.
I know, right?
Yeah, that's
So then, to go backwards, it's just reverse in terms of the syntax. Link. And then I will also change the color of this so that it's a bit easier to see. So what's also really nice is that even with the block coding, you're able to see what it would look like in Python. So if you take a look, see over here, the robot moves forward, it turns left 90 degrees, it sets the pen color to red, and then you can drive in reverse or backwards.
Mm-hmm.
And yeah, no, that's about it. That's turning and driving with the robot. So it's fun to mess around with. They have a lot of different playgrounds that you can use. So like,
Go to the castle.
Thank you. So hypothetically, if we wanted to knock down all of these towers, I invite you guys to unmute your mics, like in the chat. Actually, no, not the chat, because I won't be able to read it. I invite you to unmute your mics, or thank you, and suggest values that I could put in. So if we start with hitting the middle, I guess, tower. Any distances we want to try?
So think about how, like, unit millimeters that last time, it didn't travel very far. So obviously this number has to be a little bit bigger. Anyone would want to just name some distance, some arbitrary distance. And we can test out what you suggested, you know. Okay.
Thank you, Sophie. I appreciate you. 200. Okay. So we run. So notice that was actually pretty small. So we have to extend the distance longer. So another suggestion?
I see 600.
600.
And it does have like a little I just barely missed it. This simulation actually has like a physics engine, so it's really funny to see like kind of the robot kind of mess around with the objects and sometimes spaz out when it hits the wall. We see 450.
Oh.
Yeah. Although, you know, logically, we should probably put more than 600, but okay, we can try 450. Oh, okay, 750. All right, come on, Juan, let's see.
Nice.
Wow, you
Okay.
killed it.
Was there another tower you guys wanted to try to knock down?
So this thing of kind of like repeating and like testing code and over again is exactly what we do in robotics when we program our autonomous. We have to just keep changing values and running our code over and over again until it kind of solves our problem, you know. Kind of like how I mentioned the like first few slides, yeah. So you can see that there's 4 towers at the corners. We can't simply just go forward. We'll have to do more than that. So there are other commands out there besides going forward. I mean, what else could we use, you know?
So let's say that I want to hit the middle tower, but then I also want to hit this large tower in the top left corner. Well, right now we have it set to where it'll only go straight and it'll hit the tower, but now we have to add on to that to where we can be redirected to this tower over here. So hypothetically, we could just, instead of going through 90-degree angles and go from here to here, I don't know if you can see my mouse, we can just go at an angle to the big tower over here. Yeah. And then another random arbitrary distance you want to travel forward. Any proposals?
Let's see. I see 600.
Right. Thank you, Sophie. We hit run.
I have a feeling we'll hit it.
The robot moves forward. It does its turn. Oh, almost.
Diagonals are longer than you think. So based on this little drawing that robot did, how much exactly more do we need to add to 600? I honestly think we need to double it almost. Okay, 1050.
1050.
Yeah.
And what's really nice is as you edit it in block code, you can see it also edits itself in the Python code viewer.
Hmm. There you go.
Nice. Okay, Jacob, did you want to take it from here?
I guess I can. So we've taken a look at that little Castle Crasher challenge, but This website has a whole bunch of challenges that it's posted on its website, and we can go through a few of them. Let me share my screen. I guess a window. Let's see. It's like that. All right, do you see my screen? So I'm going to go back to the presentation. If I present, let's see if this works. Do you see it, right? Oh,
yep.
Spoiler, okay. So here's the challenge that we just did with crashing the castle. We have to knock down the towers and push the fort. Okay, well, these are things that you can do on your own. We'll share this presentation and you guys can do on your own time, do these kind of challenges. But we'll go on to the next challenge that I thought was pretty cool. So it's the disc mover, where you have to move your 9 colored discs you can see over here. Oh, I should probably click the pointer thing. Okay, so here's a little disc, and you have to bring them to the goal, you know, the right color. Let's hope you're not colorblind. So anyways, I chose this challenge because in every game, there's an element that you have to collect. You know, last year we had to collect the sky stones and like move them around and everything. In this one, you have to collect these discs, and you have to use a magnet. So you have to use this specific block of code to be able to pick up these little dots, which are, you know, these discs. And without further ado, we can get started with that. You could follow along if you want to, but I don't know, I go kind of fast, we'll see. So I already have the disc mover playground open over here. And actually, before this, I should probably show you how you can get to like the, whatchamacallit, the text code. So right now, when you open up the website, you see like the commands, but they're like in blocks. And like Lisa said earlier, we don't actually use blocks in robotics. And in general, industry never uses blocks. It's horrendous. So instead, what you'll want to do is you can see in this top right corner, there's like these greater than and less than signs, which opens up the code viewer that you know, automatically updates, right? But what you can also do is at the very bottom right, it says convert to text project. So you can click on that. You can go ahead and go here, and it turns your blocks of code into actual like you know, text of code, these programming statements. So like I told you earlier, we have our instruction, which is to drive, and we also have our little syntax as well as our parameter. Another thing that I do want to talk about is this thing before the dot. It's kind of like the object that we're talking to. So there's like different subsystems that this whole robot consists of. We have like our drivetrain, our little magnet, the pen that Risa was playing around with earlier, and also some other things about sensors and whatnot. So let's go open up the playground for the disc mover. Okay, so for this one, kind of our objective is to get our robot to go from here to here, get the disc, and then come back to the goal, and then drop it. So you'll see that on the left, we have all these commands, but they're not in blocks anymore. Instead, they're actual like lines of text. You can click on the little question mark, and I'll show you kind of an explanation and a little breakdown as to how the syntax kind of works. But I think I can just explain it here. It's pretty self-explanatory. So first off, our robot is facing towards our disk. Maybe if someone wanted to say what we could do first, because we have to get from one place from here to here. We'll have to go forward. I will tell you that one of these like squares, one of these grids is like 200 millimeters. So where is that? Okay, drive 4. How does this look? Forward. So see, I'm actually typing it out because you know, this is what you have to do in an actual IDE. However, you do see that there are autofill features. Like if I were to put drivetrain, so our little object here, when you press the dot, it will show kind of all the functions this object has. So it can drive. You can also get its heading. You can also ask questions like, is it done, as in, is it like not moving anymore? You can also set the rotation. Oh no, this is just to get the rotation of the robot. And you can also set other things about the robot and stop it completely. So we do have to drive forward. Like I told you, we need to travel 4 blocks. And I told you that each block is kind of like 200 millimeters. So, you know, 4 times 200 is 800. And then let's try it out. Let's see if our robot actually kind of reaches our little disc.
Jacob, where do you like the drivetrain dot?
Huh?
You left the drivetrain dot for the
Oh,
6th
yeah,
line.
sorry. Okay, because I was showing that example. Okay, thank you. Anyways, let's see if it runs. So it does, although it doesn't leave that pen mark because I haven't put the pen down programming statement, so I feel like we should do that. Just kind of take a look how far it travels. So pen, move, and then we have our keywords down or up. Down meaning that it's going to mark on the field, and up not. So we've made it to this disk, and remember in the presentation I showed you this new little block, although we won't be able to see that blue, it's just going to be text. So we have to go look for this magnet thing, and there it is, magnet energize. So it's just kind of like powering up this magnet to be powerful enough to pick up those disks. And you can see it kind of already autofill with boost, but you can also see that there's 2 keywords. There's boost or drop. So boost is just kind of like picking it up in the same way that you might pick up the disk in our ultimate goal game. So let's see what happens when, I guess, yeah, let's run the code now that we have our energized boost. We can see that, I thought, okay, so up here you can see there's kind of like statistics of the robot, and I thought it was going to talk about if it was holding something, but it doesn't look to be the case. To show that it is holding the disk, what I could do, I can copy this line of code. Trust me, you'll be copying a lot of code when you start programming if that's what you want to do. And this is another keyword forward, but not only can you go forward, but you can also go backwards. So if I go backwards, oh, does it not fall? Oh, it's reverse. Okay, I was confused for a second. It wasn't autofilling. But anyways, you can see how powerful programming can be. With just like one change in the code, you're able to do something completely different. With these parameters. Oh, whoops. So let's try out the code again. So you can see it goes forward. It goes forward kind of slow. I don't know what the speed of this robot is. I wonder if I can do it faster. So there's also another command that we used earlier to kind of slow down or make the robot go faster. So what is that? I think it's set drive velocity, yeah. So I think it's going at 50% right now, but I feel like we can speed this up a little more. So Drivetrain, and again, we have all these different functions. And let's say we want to select, select drive velocity, and we have to put in, I think, a number between 0 and 100. Okay, so we can put 100 and in percent. That's just kind of like our unit. So it's going at 100% of our speed. We're sending basically the most electrical signal we can send to our motors. And if we do it again, I think we should go faster. Yep, it's a lot faster. And especially in an autonomous, you want to complete as much things as you can in that 30 seconds. So it's very good to go at a max speed. But you also want to be controlled and like, say if you are going at a max speed, but like your turns are inaccurate, you do want to turn a little slower and stuff like that. So you have to count for stuff, such as that. Okay, so now we got the disk. You can see that it's gone from its initial place, and now it's at our little goal. So now what we could do is we can copy this line of code over here, or you can type it again, but in this case we can just copy it. And we have to change this keyword here from boost to drop. And what it'll do is it'll drop it, although you won't see it because robot's on top of it. So let's have the robot move forward again. But we know that we have to go forward to reach this next disk over here. But we need to know what our distance is, so we don't know what it is yet. If anyone want to give a guess as to how far it would take for this robot to get from here to here, I guess in the chat, I can't see it. Or, well, I'm just going to keep it open like this. So, if it took 800 to get from here to here, how much would it take to get to here in millimeters?
1200.
1200.
Proposed by
okay.
Robert.
Let's see. So let's just go run our code again. And it drops it. Yeah, that's basically perfect. It might look like it's over it, but I think it's fine. I think we can still pick it up. So again, we're going to have to copy this code again. And then after that, we have to copy this code again. And we know that it took 1200 millimeters to get from here to here. So it's going to take the same distance to get back to our goal. So we can just copy this. Boom. And then we will run our code again. Let's see what happens. So we got both of our disks, which is cool. And now we have to get this third one. If anyone want to put in the chat or say about how far it should take to get from here to here, or sorry, here to here. So I'm gonna have to copy this line of code again, okay? Oh, well, before that, I do have to drop the disk. I forgot about that. Okay, but now we have that. So what would this mystery number be?
1600. Thank you, Robert.
All right, thank you. 1600. And in that case, I kind of already know the answer. It is going to reach it. But we can still test it over and over again, say we didn't know about that, right? And we can also change it to 3D view. Maybe it'll show the disk in 3D that's like underneath it. Oh, okay, I guess not, because we haven't magnetized the magnet yet. Okay, so anyways, we have to copy this line of code again, okay? So now we picked it up. Now we want to go in reverse, okay? So we got to copy this again. And this time we know that it took 1600 millimeters to get to here, so just the same thing going back. Okay, and then after that, we have to drop it, and then we'll have all our, what color was this disc? All these blue discs into the goal, so we're just going to watch it from start to finish. Yeah, and it's just going to do all that. So yay, we did our little challenge for at least the blue goal, but now we have to do these other 6 discs. And already, you noticed, I was kind of emphasizing on the fact that you have to copy the code over and over and over again, and it's like the same lines of code, the same statements, the same instructions. It's like, you know, I have to type all the, because here's the thing, you can actually create kind of like shortcuts and be able to repeat these instructions over and over again without having to copy paste. They're called functions. So we can break down kind of like our little actions. So we know that every time we want to get a disk, we have to go forward a certain amount. We have to magnetize, and we have to go back, and we have to drop the little disk. So every single time we go back, we have to go back and forth, you know, magnetizing and demagnetizing. So what we can do is we can turn that into a little, like, I guess, programming statement of its own. So to create a programming function, which will do exactly all that, we do DEF, and then what can we name this? I guess disk collect. And then so far we don't really know what to do for parameters, so let's just type out what's their usual like motion when trying to get at least one of these disks. So first we have to go forward, so we know that much, so we can copy this. Next, we know that we have to energize our magnet, so you know, we can pick up the disk, so we can copy that as well. Then we have to go in reverse, so we got to copy that. And then the last thing is that we have to drop our magnet, or not magnet, the disk. Okay, so now we have all that. That is the motion that we do to go from here and back to get the disk and drop it off. So now we have all this, and I'm going to end it off with that. So you can see that we created our little function, and let's say, or how should I say this? Okay, so the thing is, every time you want to collect one of these disks, there's a different distance. And so this is why parameters are so powerful. You can create a parameter in these parentheses over here. So in this case, we can put like distance. So this distance is what we put into parentheses right here when we type in disk collect, is going to be how far our robot is going to go. So we can change this 100 to be distance, and then this 800 to be distance as well. And with that, we've created a little function that, you know, using this one line, disk collect and distance, the number, we're able to do all of this. So we can just delete all this. Like, we don't care about this because we created our new, well, not the pen move thing. Everything else can be gone. All that copy pasted code, that's yucky. We want to use the least amount of lines we can use, because, you know, the computer will have to work harder if you put more lines of code, basically. So now that we have our little function,
for the user.
it's just easier to what?
It's easier to read.
Yeah, I was going to get to that. So it's just easier to read, because you can name your functions to basically be, you know, whatever you want. We know that if I were to type in disk collect, I know that I am, you know, our robot's going to collect a disk. But what we need to put in our parameter is kind of how far we need to go. And from earlier, we remember that going from here to here is 800. So if we put 800, that will collect the disk and it'll come back here. And I just have to repeat again. So disk collect, and this time it was 1200, I believe, and then disk collect, and this time it was 1600. And with that, it will actually do the same thing, but now we did it in less lines of code, hopefully. So you can see how it goes back and forth using less lines of code and using our new function that that we've created. And with that, it's so much more readable because you know that this collect, you're going forward this distance, you collect the disk and you go back. And with that, you're able to continue on with the rest of the other 6 disks. You just have to turn around and do the same thing again. In fact, you can even put functions inside of functions. So what you could do is you can do another one. You can do like disk collect row, and in this one you can put disk collect, or well, I can just copy paste it. You can do this. So programming becomes really interesting when you start finding all these ways to make your code like shorter and more abstract. So now instead of this, I can literally just put disk, or wait, did it say row or column? It should be column. I'm dumb. Anyways, we have our little column, disk collect column, and with that, it's going to do literally the same thing, hopefully, and it does the exact same thing. So now I know that when I read this one line of code, or when the robot reads this one line of code, it knows to do all of this. So with that, it's going to be very easy to just get these other 2 columns of disk. Basically, I just have to turn right. So drivetrain, turn, and then I can put the keyword right. And then after that, I need to travel, let's see, how many blocks is this? 1, 2, 3, 4. So what I could do is drivetrain, drive for, and then we know we need to go forward, and we need to go 800, and then our units. And then we just need to drive train turn left, so we're facing towards our disk in the next column, and then let's see what happens. So we run all this, and again, this is why I wanted to speed up the process, because if this wasn't at 100% speed or velocity, this thing would take forever. Okay, is that doing that again? Oh no, what is it doing? What is it doing? Okay. I think I've made an error in my judgment. Okay, so I think in this case, what happened, so this is what happens when you're a programmer. Sometimes you assume things to work, but really your logic is flawed. Remember that the computer is never wrong, and it only does exactly what you tell it to do. So you're always wrong, and you have to figure out what's wrong with the code that you've written. So in this case, I told it to go right, but it didn't really turn right. It just went straight. And I can explain why, because you're reading code from top to bottom, and what it's going to do is it's going to read this disk collect column. After that, it's going to be told this instruction turn right, but there's no like line of code to tell it to wait until that like turning right motion is done. So you do have to put either a line. Let's see, and I know there's a way to just turn with degrees, but this is a good example right here. So we know that there's no waiting between turning right and going forward, so we have to put a little like waiting thing. What is it called? Wait. So you can put wait 1 second, and then it'll actually turn enough so that it faces in that direction. But in this case, we want to turn exactly 90 degrees, so we can just do turn for right 90 degrees. And we can do the same thing. Oh wait, we can do the same thing over here. Turn that to the left. And with that, that should be able to fix the problem. Let's see. And there you go. It's literally pretty much in the exact same spot as it was over here. And now all we have to do is just put in this one line of code, and it does this whole column. And after that, to just repeat, these 3 lines of code, which you could even put in a function in of itself. So it's, again, functions are really powerful, condensing your code and everything. It makes things so much easier. But I think you guys get the idea as to kind of how functions work, and it's pretty powerful. even if you're a little confused now, don't worry. If you stay along with us, we'll explain so much more into this whole abstraction thing. And with that, we're pretty much done with that challenge. So I'm going to go back to the presentation. So we've learned about that, the repetition of commands. What can we do with that? I just told you when you have all these repeated commands that are like similar to each other, you can create functions and parameters that make these commands a little different. Okay. So we can go to our little next slide. Oh, and it's me again. Okay, but this time I just want to do something a little fun. So far we've programmed robots to do exactly what we tell it to do, but you can also make it so that robots can decide what to do for themselves, kind of. In this case, this robot is kind of like a Roomba. So it's going forward, and then once it reaches like the wall, it has a sensor that kind of detects when it's close to the wall, and then after that, it's going to decide, hey, I want to turn in a random direction. So this is pretty fun because you can kind of make like art pieces with it, kind of. So yeah, and by dead reckoning, that's what I meant. You program it to do exactly what you tell it to do because you already know what it has to do. But sometimes, the robots have to make decisions for themselves, such as the flow chart that you saw for the autonomous in the presentation earlier, counting the number of rings and having different instructions based on that. So this isn't, okay, well, where's that thing? Oh, so anyways, here's what the actual thing looks like if you keep it running. I think it looks pretty cool. I'll program it from start to finish though. So if I can open up a new thing, let's see, convert to text project. So we can play around with this little idea of being able to let the robot decide for itself what to do. Let's go back to our grid map where it isn't really too much. So exactly how do we go from just going forward to doing all this crazy stuff with turning and everything? So kind of my thought process when I started doing this was I know that I needed to use a sensor to detect when it's close to the wall. So I'll have to use, let's see, I'll have to use this a little distance.getDistance instruction, which will give us the number of like how close. Actually, it is this. So this line of code right here is the same thing as this. So I want to use like a little comparison to say that if this distance, from here to here is less than like 100 millimeters, then we need to tell the robot, hey, don't keep going because you're going to crash. Instead, you should turn. To start this off, since you want to keep running this forever, oh, where's our little saying? Since you want to run this forever, you can see that even though the amount of lines of code I have is very minimal, it definitely drew a lot. So to get started with this, what you'll want to do is you want to do this is called a while true loop. So basically, the code inside of this while loop will run forever. And so, yeah, it's basically just while, like, okay, sorry. This thing right here is going to be kind of deciding whether to run the code or not. And if you pick true, it's just going to run the code inside of the while loop no matter what. So now we can get started. So we know that we have to go forward, but we know that we can't go forward forever because if I just start, drivetrain, drive for, that's a little clunky. I want to move down here. Drive for and then forward. We don't need to really specify direction, huh? Actually, I think we can just tell it to go forward. Okay, so we know we have to start off with that. Oh, and again, it's slow. Okay. Oh, and the program stopped. Nice. Because, a loop without a wait statement. Okay. So we do need to add a little wait. We'll have to put like 5 milliseconds, I think, so it won't show an error. So before that, we need to set the speed of the drivetrain to velocity. So set drive velocity, and we want it to go at 100% speed, because again, it's slow. So now that we're going forward, and we have our little thing to make sure it's not going into any errors. It goes forward, and you can see what I meant, the physics and everything. It's just gonna, it just flipped over. So we don't want to do that. Instead, we want to use our little sensor to be able to turn around. So what we'll have to use is another control structure. We have to use, let's see, what did I use last time? Well, let's say, no. So we actually have to do another while loop. And in this case, while, and then we have to use our little get distance over here. You can drag it here. So this will report just what number is right here. And you'll, okay, let's play it again. Oh no, wait. It's because I added this. Can I comment it out? Okay. So you can see that as the robot gets closer to a wall, our distance decreases until it's, yeah. Okay, so now that we know that, getting closer and closer to a wall, but we don't want it to get hit. So let's say as long as our distance between us and the wall is more than 100, then we can keep driving forward. So, oh wait, no, I can just indent right there. So you can see that this number right here, once it gets, if it's greater than 100, it's going to keep driving forward. But then after that, we want to do something different. So we do want to turn around, but what's cool is that you can decide kind of where to turn using what's called a random number generator. So let's see, we want to turn. So drivetrain, turn 4. And for this, well, you can just put right or left, but it doesn't really matter. And then after that, you can put, okay, hold up. If I can open up, or no, I can just do this. Direction, angle, units, weight. Okay, so right. And then after that, instead of putting just a number, you know, like how many degrees you want to turn, so 120 degrees. Well, we are going to use degrees, so let's put that right there. Instead of 123, you can just replace that with any single statement that will return a number. So what you could do is you can use this random object, which has this statement called randint. And in the parentheses, you can give it a range of what numbers it will output. So in this case, okay, so we hit the wall and then we want to turn in a random direction, but we also don't want to like turn too little and like, okay, how do I describe this? Let's say, you know, if I put 90, you'll see that once I hit the wall, or no. Oh wait, when I wait statement, shoot. I guess I have to add that again, huh? Okay. This is kind of the weird thing about working with, what do you call it? Like a text instead of syntax, because syntax kind of like catches all the errors for you, or not syntax. Blocks catches most of the errors for you, but when you're working with, you know, an actual like with text and everything, you get those kinds of errors. So let's see if it just runs now normally. Yeah, it does. Oh wait, no, I should have done it less than 90. Never mind. So if I put like 60, you'll see that it's still going to hit the wall, but we want it to turn away from the wall, pretty much. And see, we didn't want to do that. We want to go away from the wall. So what we need to do is this number right here should probably be greater than 60. Probably greater than 90 as well, because we don't want it to go perpendicular with the wall, or sorry, like parallel with the wall. We want to get it away. So in this case, we're going to go back to our little random object, randint, and we can give a little range. So we know it has to be more than 90. So I honestly don't really know what number to put here. So if anyone would want to give a number just greater than 90, but not like too high, like if anyone wants to say a number, I actually don't know. Like it's kind of like you just have to play around with the numbers. So any number, 120, okay. So 120 is like our minimum. Like this is the minimum amount of degrees that a robot's going to turn after, you know, reaching close contact with the wall. So this is our minimum. Now we also have our maximum. So, you know, if anyone want to name another number that's greater than 120, preferably like a large difference. So not like 125, but like more than that, because we want it to kind of have a large range of motion where it could possibly turn. So a lot more than 120. Okay, well, Juan was first. I saw 300. So now we put that. Let's hope it works. I think this should work. Okay, I don't think I put the pen tool yet. Let's just see what happens without the pen. I will put that logic in a little bit. So see, now it kind of turns away. Oh, it's just going in circles. That's fun. Okay, now it's going in another direction. Let's see. See, so now it's not, you know, hitting the walls. It's actually getting away from it pretty much. Yep. So it's kind of like our little Roomba. It's just kind of roaming around our little, I don't know, a little room, living room. Okay, so we're done with that. Now let's have our little pen tool open. We'll have, so we're going to talk to this pen object, and we want it to be down. So we want to start writing it. And we also want to, have a certain color. So if anyone would want to like name a color, well, okay, there's actually only 4. So, oh, whoops, let me open it back up. What color should I do? Green, okay. So if I put green, let's see what happens. And see, it starts drawing this green line. And now it's just gonna kind of start drawing. And you saw, oh, okay, it's going around in circles again. Oh, and now it's going like basically 90. But over time, it's gonna randomly go in like basically all directions. And it will eventually fill up this little field, kind of like, oh, did I clear it? Like this. But you'll notice that I actually have 2 different colors here. So I'm just gonna kind of start coding on how to like do that thing, on how to have 2 different colors. So we can alternate between 2 different colors. So before this whole going forward thing, I would go decide what color I want to use for our pen. So I'm going to use what's called an if statement. And then basically it's just kind of asking a question inside this little parentheses, is this statement here true? So I'm going to use what's called a toggle. So I'm going to use this little my variable here. And I'm going to just ask if it's equal to 0, okay? And if it's equal to 0, and you'll see that we have a little statement up here that is telling it that my variable is currently at 0. So it will read this line of code. In this case, I want to set the color to green again. Oh, whoops. There you go. And then we have else. And what we can do is, for this toggle to work, we need to change the value of our variable. You can also use what's called a Boolean. So instead of using 0 or 1, you can also use true or false values. But I mean, my variable thing was already there, so I'm using it. Anyways, now we already included our color green, but what's another color that we can use for our little thing? Is there a purple? I wish, but this it's very limited. There's really only, like I said, 4 colors, and I've tried looking for like RGB values and whatnot. Okay, black. I saw that first. Well, okay. Does anyone else want to like contest? Because I saw, I think 2 blue. Because maybe I'll do majority. Maybe I'll do majority. Okay, no, it's 2 black, 2 blue. Does anyone else? I'm gonna count up to like 10. Does anyone else want to like blue, blue, blue? Okay, it looks like blue might actually be better in this case. Oh, sorry, Juan. I gotta do blue. Okay, because everyone wants that. Okay, so that's gonna be our other color, and then my variable, I'm going to set it to 0. So kind of the reason why this works, how it alternates between one or the other. So it's going to go read this statement, and then it's going to change the value of this my variable. It's going to become 1. And that means this statement is actually going to be false. And in an if else statement, if this statement is false, then no matter what, it's going to read this, these lines of code underneath the else statement. And in this case, it's going to set our color to blue, and then my variable back to 0, which then makes this statement true. So the next time that this code is read, it's going to read these lines of code, and then the next time this code is read, it's going to read these 2 lines. So it's able to alternate between one or the other. So now, okay, what did I do this time? All right, debugging. What did I do? It doesn't really tell me any. Oh wait, no, I have to look in our little console. My variable equal. Oh, okay. It's very useful to have an IDE, like Risa said. It tells you kind of like what errors there are, in your code. So I had to put 2 equal signs, because 1 equal sign is to assign this value to a variable, while this 2 equal sign thing is a comparison between this and this. So my variable, okay, it's 0. 0 equals 0. Is that a true statement? Yes. And this should work now. So it's just going to start kind of doing its own thing, and now it's going to alternate colors. So now we have blue. I wonder if there's other options for the pen tool, if we can make it like thicker. It doesn't look like it. I only see 2. Oh yeah, you can also check again like what, oh, I should probably keep it so you guys can watch it. You can also check again what, what options you have in terms of like the object you're talking to. So there's really only 2, which is a shame. Maybe it'll add more stuff later, more colors, especially because it's kind of boring. But yeah, you can see in the 3D view, just kind of strolling along. And this is something we can achieve, actually with our robots. Like, if we have distance sensors and we program all the right logic. We can literally do this on our little field if we wanted to, actually. Although it'd probably be not so great considering that you really don't want the robot to hit the wall, and maybe the ultrasonic sensor or whatever we use for distance to calculate distance isn't accurate, and yeah, our robot's gonna hit the wall. And also we can't mark the field, and we can't draw all this stuff. It's pretty cool. Yeah, we got green and blue. We got a little rave going on, I guess. Honestly, yeah, that's basically all I have for this little presentation for the VEX VR stuff. It's pretty cool. This robot's deciding itself what to do. I did not tell it to go this specific direction. The code was kind of able to just guess a number, or pick a number, I mean. And yeah, it just keeps on going. And yeah, oh, okay, it's just kind of going 360. It's kind of like dancing, okay. And then yeah, like I said, you can run it for a while, which I did, and it kind of made this behemoth of a mess. And yeah, that's basically it. I don't really have too much else. Risa, if you have anything else to say.
Yeah, no, I'm good. Tyler, are you?
I fixed
Were
it.
you able to? Okay.
I fixed it. It's good. All right.
All right, so I'm gonna.
Yeah.
How do I stop this? Stop presenting. Well, yeah, that's my little program that I did.